Good morning, doctor. My name is Wong Kao Ho, ID KH23036. And now going to present the introduction. This project is going to design a new methanol production plant. Methanol is a primary liquid petrochemical that is important in chemical and energy industry due to its ease in transportation and storage. In this project, we're going to use Aspen Plus as our use to simulate the process and AutoCAD for the plant design and layout. The method that we use to
Today,
produce
I will
methanol
briefly walk
is
you through our
biomass
experiment simulation for
because it
methanol
is
production
using
using the
renewable
biomass
energy source
gasification. There are
from
six main steps.
animal and
The
plants,
first one is we
such
begin with
as
a
wheat,
simulation
barley,
assumption
rice
where we
husk,
assume
food
that this
waste,
is a
and dead
steady-state
beets.
process, which is why model using the
From that, we
Penrose-Benson
can
equation of state,
lowering the
with all
greenhouse effect
chemicals
and
reaction
also
assumed to
the
be at equilibrium.
decrease
Then the
the
combustion and
waste.
gasification blocks are modeled at isothermy,
Biomass
which
is
means
a
there's no
carbon neutral
pressure and
resource
temperature difference throughout the
because
process, and all
it can be
unit operations
generated
are treated as
within short
zero-dimensional,
period if
meaning they
managed
have uniform
in a
temperature
good
and
way.
perfect mixing. Our biomass
Good day to
feedstock
Doctor and
is dead
everyone.
pits,
I'm
as
Giri Kumar,
it gives the highest methanol yield
I would
of
like to proceed with the
0.82
AutoCAD, which
kilograms
is
of
the cyclone
methanol per
separator.
kilogram
Our design
of
process
biomass,
started with the
as
initial hand
reported
sketch
by
as shown
Roy
on the
et
left
al.
side
in
of the slide.
2024.
In the sketch, we
The
illustrated
feed is
that the
first
basic
dried
concept
at
and flow direction of the
100
biogas
degrees
system.
Celsius in
The
1 bar
biogas enters
using
from
an
the side as
R-stoic
converted biogas
reactor.
from R stoic, and
Next,
due to the
in the
cyclonic motion
gasification
inside the
section, the
separator,
dried
the
biomass enters
moisture
a combination
and
of
heavy particles
R-yield
are
and
forced to
R-kits
exit the
reactors,
wall at
which
top.
was operated at
Meanwhile, dry
800 degrees
biogas
Celsius
exits
and
at the
1 bar,
bottom.
where it
On
is
the right, we have the
decomposed
detailed
into
AutoCAD
elemental
drawing. This
components:
technical representation
carbon,
includes the precise
hydrogen,
dimensions and
oxygen,
geometry shapes
nitrogen,
based on
sulfur,
standard design
ash, and
practices
water.
for cyclone
Steam
separators.
was also
We used
injected at
AutoCAD to
100
ensure
degrees Celsius to
accurate
facilitate the
proportions,
gasification
suitable
reactions.
flow
We
paths, and
modeled
proper
key chemical
functionality.
reactions
Key
such as
dimensions,
the
such
combustion,
as
which
the
is C
cylinder
plus
height,
O2,
cone
partial
height, and
oxidation,
inlet diameter are clearly indicated for
Bordeaux
construction
reaction,
and analysis
then
purposes.
water gas
Cyclone
shift and
separators are widely
methylation.
used in
These
industrial
steps
applications
generate
for
a
gas-solid
hydrogen
separation
rich
due to their
syngas.
simplicity and high efficiency. That's all from me. I would like to proceed to the next presenter.
A fluidized bed gasifier reactor used in biomass gasification is a system designed to convert solid biomass into a combustible gas called syngas. It achieves this by suspending the biomass particle in hot, inert bed material using an upward flow of gasifying agent like air or oxygen or a mixture. The core of the system is the fluidized bed. A gasifying agent is blown upwards through a distributor plate at the bottom of the reactor. At a certain velocity, this gas lift and suspend the solid bed material and biomass particles, causing them to behave like a boiling fluid. This creates an excellent mixing and uniform temperature distribution throughout the bed.
So I will continue for the heat exchanger drawing. So this is the initial hand sketching drawing for the heat exchanger. So these two drawing are drawn by using the AutoCAD. And for the left side is for the detailed drawings, and for the right side is part and assembly drawing. So for this mini project, we use two of the heat exchanger for the plant design. Even if the heat exchanger are suitable for the heater and also the cooler, but both of the heat exchanger used in the plant is act as the cooler. And the function of heat exchanger basically is to change the temperature between two fluids.
Good morning, doctor. And now I'm going to present about the last part of the model in Aspen, which is the rector asteroid. For the left hand side is the hand sketching drawing for asteroid, and for the right hand side is the detailed drawing of asteroid by using the the AutoCAD. And the last one, the second one, is also by using the AutoCAD but it's a part of it. So asteroid block is in Aspen is used to model the chemical reactors where the stoichiometry and conversion of the reactors are known, but reactor kinetics as no needed.
Next, I would like to proceed with the Expand Plus process flow diagram. This is the overall process flow diagram for methanol production from biomass by using the gasification. The process starts with biomass drying, where moisture is removed. Then, the dried biomass enters the gasifier, where it reacts with steam to produce syngas. Then, the ash is separated from the syngas, and then the clean gas is cooled and compressed. The compressed syngas enters the methanol reactor, producing a mixture of methanol and unreacted gases. This mixture is cooled and separated. The methanol-rich product exits as the final product. Unreacted gases are partly recycled, with the rest released as off-gas. This diagram summarizes the full process, and I'll explain each stage in more detail next. Today, I will briefly walk you through our experiment simulation for methanol production using the biomass gasification. There are 6 main steps. The first one is we begin with a simulation assumption, where we assume that this is a steady-state process, which is why model using the Peng-Robinson equation of state, with all chemical reactions assumed to be at equilibrium. Then the combustion and gasification blocks are modeled at isothermal, which means there is no pressure and temperature difference throughout the process, and all unit operations are treated as zero-dimensional, meaning they have uniform temperature and perfect mixing. Our biomass feedstock is date pits, as it gives the highest methanol yield, about 0.82 kilograms of methanol per kilogram of biomass, as reported by Roy et al. In 2024. The feed is first dried at 100 degrees Celsius and 1 bar using an R-stoic reactor. Next, in the gasification section, the dried biomass enters a combination of R-yield and R-Gibbs reactors, which was operated at 800 degrees Celsius and 1 bar, where it is decomposed into elemental components: carbon, hydrogen, oxygen, nitrogen, sulfur, ash, and water. Steam was also injected at 100 degrees Celsius to facilitate the gasification reactions. We modeled key chemical reactions such as the combustion, which is C plus O2, partial oxidation, Bordeaux reaction, then water gas shift and methanation. These steps generate a hydrogen-rich syngas. Then the syngas conditioned using a cyclone separator to remove solids and was cooled to 120 degrees Celsius using the heat exchanger. Then a multi-stage compressor was utilized to raise the pressure for the synthesis reaction. In the methanol synthesis reactor, which uses a cuprum zinc oxide as catalyst, carbon monoxide and carbon dioxide are hydrogenated to produce methanol via 2 main reactions, which is carbon monoxide and carbon dioxide. The resulting stream, known as stream S14, goes through the purification process, where the unreacted gases such as carbon monoxide, hydrogen, and carbon dioxide are recycled back to the compressor to improve efficiency and reduce the waste. Finally, the process achieves a methanol purity of 94.42%, making it suitable for downstream applications. Again, this simulation highlights the potential of biomass gasification as a sustainable route for methanol production. I would like to pass to the next presenter.
So I will continue for the experiment class result. So as said before, the biomass that we use in this mini project is dead pits. So the inlet flow stream, which is biomass, it have the temperature of 40 degrees Celsius and pressure of 1 bar. For the product stream, the temperature is 50 degrees Celsius and pressure is 10 bar. So the total mass flow for biomass is 1000 kg per hour, while for the product is 813.584 kg per hour. So since the product we want is methanol, the methanol has the mass flow of 768.15365 kg per hour, which the mass fraction of the methanol is 0.9441605, which is it's have the conversion of 94.41%, which is high. Next is the case study to increase yields and decrease the energy consumption for the plant. I have 3 cases that we've studied in this mini project, which the first one is the purge value. We have changed the purge value from 0.75 to zero point 0.1, and the mass flow decreased from 768.148 to 631.238. This shows that if we want to increase the methanol yields, we should increase the purge value. The second one is temperature. We change the temperature of cooler 2 from 50 degrees Celsius to 60 degrees Celsius. And the mass flow are decreased from 768.154 kg per hour to 734.547 kg per hour. At the same time, the heat duty are also decreased. So if we want to increase the methanol yields, we should decrease the temperature. However, if we want to decrease the energy consumption, we should increase the temperature of cooler too. The last one is pressure. We change the pressure of separator, valve, and also the cooler too from 10 bar to 20 bar. And the mass flow increased from 768.154 to 795.929. And at the same time, the heat duty are increased from 499.157 to 500.899 kilowatt. However, the heat duty are just slightly increased, so we can conclude that if we want to increase the methanol yields, we should increase the pressure.
Okay, so in conclusion, this study focused on designing a methanol production plant using biomass gasification with the help of Aspen Plus for process simulation and AutoCAD for plant design. Among the other methods, biomass gasification was selected as the most suitable pathway as it can maintain the resource sustainability and had many environmental advantages and due to its technical feasibility. The process utilized dead pits as the biomass feedstock due to high methanol yield. The overall process involved multi-stage biomass gasification, which includes pyrolysis, combustion, and gasification zones in the fluidized bed gasifier. The Aspen plant simulation employ RSTOID and uh, RSTOID for combustion and RGIPS for gasification, assuming steady state equilibrium chemical process and isothermal blocks and using the Penrose equation of states. Afterwards, the raw syngas went through a comprehensive purification to remove impurities like particulates, tar, acid gases, and inert gases. Then the treated syngas was fed to the methanol generator, where CO and CO2 are hydrogenated to produce methanol. Unreacted substances like hydrogen, carbon monoxide, and carbon dioxide are recycled back to maintain the efficiency and reduce waste at the same time. To optimize the process, case study were conducted and shows that by increasing the purge value significantly from zero point 0.1 to 0.75, the product methanol mass flow will increase from 631.238 kg per hour to 768.148 kg per hour. Other than that, by increasing the cooler's outlet temperature, it can decrease the energy consumption, but at the same time, it reduce the methanol yield. In contrast, raising the pressure from 10 bar to 20 bar from the separator, valve, and cooler increase both methanol production and the energy consumption. By the end of this study, the final mass purity of methanol was managed to obtain, which is 94.42%. And that is all from us. Thank you.